Welcome all. Today we are going to discuss the unit 4 of our subject advanced manufacturing processes. Name of the chapter is visible on our screen as micromachining and nanofabrication techniques. So let's see its introduction. So in today's high technical engineering industries, the designer requires for the component which are strictly according to the standard given in international market or designed by the scientist or researcher. So these properties may be in the form of extraordinary properties of materials such as high strength, high heat resistance, hardness, and corrosion resistance. So the complex 3D components such that turbine blades which are to be manufactured in day-to-day industries. This is the need of today's engineering field, that they need to develop more and more complex 3D component. Then avoid the failure. Fiber for food processing and textile industries having a few tons of micrometers as whole diameter and thousands in number. So in that food processing industries, the material we use, this material actually work under microprocessing, and they are having a lot of micrometer holes, few tons of micrometer holes, and the working on these are really too small. This cannot be performed by conventional machining, so we took this concept under advanced manufacturing processes. The nano level surface finishing on complex geometries which are impossible to achieve by traditional method. For this purpose also we need to do advanced manufacturing, which machining cannot be performed by conventional one. Such feature of component can be achieved only through the advanced manufacturing processes in general and in advanced machining processes in particular. Okay, so let's see the another slide. Here we are trying to compare the micro manufacturing. Just see that what is 100 micrometer. It is the paper thickness or human hair. uh, we are taking this slide just to explain that how micro machining we are going to conduct. For this example we are just taking this, that 8 micrometers is equals to red blood cell capillary. 0.5 micrometer is the visible light or machining tolerance. 0.07 micrometers is equals to 210 IC production design rules, and 0.0003 micrometers is equals to atomic spacing in solid. These are the thickness which can't be visible by our naked eye, so we have to do all this machining, which is called as micro machining. For this purpose we need to do advanced manufacturing processes. So there are two type of material removal process. First one is micro or nano machining, another one is a macro or nano finishing. Machining can be taken by two process: traditional machining process and advanced manufacturing process. Same way, finishing process can be done by traditional as well as advanced finishing process. Here are the finishing process distinguish here traditional and advanced. In traditional you can see that grinding, lapping and honing. Grinding simply can be done by the grinding wheel. Lapping, it is done by conventional tool, and normally lapping is done for the sitting arrangement in walls industry. And honing is produced by using the tool which is named as horns. And in advance there is the AFM, MAF and MRF. AFM, abrasive finishing machining process, and MRF, these are the processes for advanced manufacturing process. Next check. Properties of work material to be machined. So applicable for electrical conducting materials. These are the types of micro machining processes. We are going to classify it. First one is based on the application of only for electrical and conducting material. Second one is the application for both electrical conducting as well as non-conducting material. Example for this kind of machining is USM, ultrasonic machining, AJM, abrasive jet machining, LBM, laser beam machining, and etc. And fourth one is the application for non-magnetic material. For this they are having MAF, MRF, etc. And for thermal conducting and reflecting material also plays an important role in some cases, such as laser beam machining. Okay. So here we are going to discuss the problems in micromachining. The problems in micromachining is listed on this, that first one is the mechanical deformation, second one is the thermal deformation. As you are going to do very micro machining, so the tool you are going to use is also very small in this, small in design, small in shape. So that's why if there is a production of heat, then thermal deformation in this occur. Then surface integrity means sometimes your tool get fixed in that surface way which is working, so problem of the surface integrity. Then gap between the tool and workpiece. Actually this gap you have to while doing the machining. In our previous chapter 3 we saw this, the gap which is kept between the tool and the workpiece should be very small, so that only electrolyte pass it in the none of the tool is comes in directly contact with the workpiece. So this keeping to keep this gap is also a problem in micromachining process. Then shift in tool handling. The tools which are used for micromachining are very delicate ones, so during handling or during the placing of these tools we need to take some much more precautions. So this is also a problem in micromachining process. Let's see, these are the types of micromachining process which we are going to study. First one is the abrasive jet machining, another is the abrasive water jet machining, third one water jet micromachining, and ultrasonic micromachining. Today we will discuss the ultrasonic micromachining in deep. This diagram simply shows the what is difference between water jet machining, abrasive water jet machining, and abrasive jet machining. First one, in water jet machining you can see that only water is forced on the workpiece. Here workpiece is in the form of wood, stone, soil, and aluminium. So on in water jet machining only water is forced on the workpiece. In abrasive water jet machining, water along with the sand, which is in compressed form. Compressed water and sand are focused on the workpiece. And in case of abrasive jet machining, compressed air along with abrasive material is forced on the workpiece. This is the basic difference in water jet machining, abrasive water jet machining, and abrasive water jet machining. This is the principle of mechanical advanced micromachining. Mechanical advanced micromachining, here what on which principle it works? It works on the principle that fine abrasive particles with high kinetic energy hit the workpiece at an angle and remove the material in the form of micro and nano chips. If the kinetic energy of the abrasive particle is high enough, then it will remove the material by shear deformation in case of ductile workpiece, and material uh, by brittle fracture in workpiece material is brittle. So this is the basic principle that during this advanced micromachining processes we are just removing the material from the workpiece, and we are performing this machining here. Okay. Now, what are the applications of this micromachining can be listed here, that hole up to 86 nanometer tip. Nano means 10 raised to power minus 9. So dip can be drilled without employing special techniques. Microbursts are clearly visible, so microbursts can be removed by uh, advanced micromachining processes. This process is also useful for producing micro cavities. Suppose we want to produce cavity which can be produced by traditional processes, then using this advanced processors, we can produce the microcavity in the desired format on the workpiece. Uh, Now come to this topic. What is it? Is ultrasonic micromachining process. So this the diagram shows the components of ultrasonic micromachining process. Here you can see the in bottom there is a pump, and through nozzle we are focusing this abrasive material on this workpiece, and on the main component you can see that transducer, coupling and horn. This horn is coupled through the transducer, so that this can make the vibration there and produce the vibration, and using that vibration the abrasive material can micro machine the workpiece. The transducer is connected to the vibrating control unit and power supply. Transducer actually converts this electrical energy to vibration energy, and coupling is used to join this horn along with the transducer. The main component of this ultrasonic micromachining can be stated as a power supply, acoustic head, CNC controller, micro tool, then the abrasive slurry and the workpiece. Okay. uh, Discussing about its working principle, it can be stated that when the vibrating tool head hits the free abrasives in the slurry, they are set in momentum which provides an impact on the workpiece surface. On continuing the repetitive impacts, localized fatigue stress is developed, resulting in microchipping and hence removal of material from the workpiece. Here what function of pump is just put that abrasive slurry and again uh, pump it to the nozzle, then through this nozzle this abrasive slurry goes to the workpiece and horn, producing continuous vibration which gives impact on the slurry, and slurry removes the material from the workpiece. Okay. Then discussing about the parameters can be listed as material removal rate, surface finish rate, then tool wear rate, then machining accuracy, aspect ratio, and the current ratio. These are the significant parameters which affects the ultrasonic micromachining. The process parameter which influence the process performance. Um, I already mentioned the name in this before. So let's come to the application. Using ultrasonic micromachining, a square, triangular, and a circular macro holes on silicon plate cords having size as small as 20 can be obtained. Blind hole can be obtained with the help of ultrasonic micromachining having accuracy up to 10 nanometers. So, using ultrasonic micromachining, array of pillars, an array of micro holes having diameter 18 can be produced. Okay. Then this is the focused ion beam machining. What is focused ion beam machining? In focused ion beam machining, an ion beam which specific diameter and intensity is directed to a sample surface for removal of material in nanoscale. Okay. What is occurring in ion beam machining? That there is a sputtering of occurs. Sputtering of means knocking out atoms from the workpiece surface by the kinetic momentum transferred from incident ion to the target atom. Removal of atom will occur when the actual energy transfer exceeds the useful binding energy. What is the main principle of this focus ion beam machining? That when you are focusing ions which is having energy more than the binding energy of the atoms in the workpiece, then it starts sputtering the atoms in the workpiece and produce the machining which is required there. The diagram itself shows that working parameters can be the kinetic energy of the incident ion and incident angle of this ion on the workpiece. So in this way our focus ion beam machining works here. Okay. Then comes to the application of focus ion beam machining. Focus ion beam machining can be used in micro and nano machining because of small material removal rate. One of the important application is preparing sample for transmission electron microscopy. Focus ion beam milling has an ability to produce of ultra thin and uniform lamella that are electron transparent and can be used for sample preparation. FIB machining is used in manufacturing atomic force microscopy because of precise controlled ion milling of the sample. FIB machining is used in size and shape control of nanostructure of microcomponent in nanosemiconductor component in electronic industries. It is also useful in lithography process. After this, the remaining topics will be discussed in the next lecture. Thank you.